welcome to our weekly Oxford seminar. It is my absolute delightful delight to welcome our own David Jaz Myers here to speak, who's going to be talking about a modal proof of the nerve theorem using simplicial arguments in cohesive homotopy type theory. Please, David, start speaking.
Thank you, Tim, for such a wonderful introduction. It's good to be here at our own seminar. Yeah, so I'm going to talk today about the nerve theorem. This is a classical theorem that I'm going to describe shortly, and then the proof we're going to give here uses cohesive homotopy type theory. In particular, it uses a kind of multiple different cohesions interacting in a type theory that was developed by Mitchell Riley and myself. And this is sort of one of our examples of how you can sort of dip into new kinds of mathematics in the middle of an argument, synthetic mathematics, I should say, in the middle of an argument. And so, yeah, let's get started. So what is the nerve theorem? So the nerve theorem is a way of computing the homotopy type of a space. So the nerve is a simplicial complex which is associated to an open cover of a space. And what you do is you take an open cover, like there on the left. And then what you do is you add a point for every open in the cover. And for every intersecting pair, you add a line. For every triple intersection, you add a triangle. And every quadruple intersection, you add a tetrahedron, and so on. For any n-fold intersection, you add an n-simplex into your simplicial complex. The way to define that is to say that you have an n-simplex whenever the n-fold intersection of those corresponding points is inhabited. So the theorem, the classical nerve theorem, it goes back, there's a number of versions. I think the original was due to Alexandrov. But the one I'm going to mention here is Laray's version, which says that if you have a quote-unquote good open cover, which is a technical term, then the homotopy type of the space may be computed as that simplicial complex, the nerve of that open cover. Now, what it means for the open cover to be good is that the n-fold intersections of any opens in that cover is contractible. Right? So this is an example here of a good open cover, because if you look at the intersections, they are still contractible. They're little blobs. That's the main idea. So now the way that this that we're going to approach the nerve theorem here is to understand that there's actually an intermediate step between the open cover, or the space, and the open cover, and the simplicial complex, which is something that is both spatial in the sense of being like made out of spaces, and simplicial in the sense of being organized out of simplices at the same time. And that sort of here, you might say, could be represented by this middle point here, and that's going to be the Czech nerve as opposed to the Alexandrov nerve of the cover. So the nerve theorem is about computing the homotopy type of a space. So before we go into how we can prove the nerve theorem, and sort of, as we'll see, generalize the nerve theorem, we have to ask ourselves, what's a space and what's a homotopy type? Right. So the first step to understanding this is that these are not the same thing. A space is not the same thing as a homotopy type, and a homotopy type is not the same thing as a space, despite the fact that in usual ways that algebraic topologists talk, they often conflate the two, right? But it's very important for us to separate these. In particular, the real line is a space. It presents a homotopy type. The homotopy type the real line presents is a point, because the real line is contractible, right? There are many continuous functions R to R, and they're different. It's important to note that they're different. A lot of math rests on the fact that there is more than one continuous function from the real line to the real line. However, of course, there's only one function from the point to the point. These are really different things. So taking the homotopy type is an operation that you do to a space, and you get the homotopy type out of it. So the real line gets shrunk down to a point. The n-sphere gets shrunk down to the homotopy type of the n-sphere. right? Which is just, this is to emphasize, this is the space, right? And this is something that we'll come to later, like to understand exactly what this could mean. And right, yeah, so taking the homotopy types in operation. So what is a space? We're going to go back to Riemann. Riemann has a really good introduction to what a space is in his, I believe it's his habilitation. It's a 16-page report he did in I think 1850 something, where he invented Riemannian manifolds, right? And he settled the notion of it's an incredibly far-reaching paper where, in addition to giving the notion of metric, he also made some observations that in fact that the metric of space-time, so whether we are in our space for him, right? Whether we actually space actually satisfies the laws of Euclidean geometry, or whether it is spherical or hyperbolic, elliptic or hyperbolic. That's an empirical question, and he actually writes that in this. He also says something even more far-reaching, which is he also says that since the very idea of rigid rods, which is used conceptually to give the idea of the metric, fails in the infinitely small, it may be that at a certain level of smallness, the basic notions of geometry, in particular, the various relationships between the coordinate functions, may fail to hold. And this is something that is sort of borne out in modern physics, where we find that there's both the commuting coordinates of the bosons and the non-commuting coordinates of the fermions in the very small. So extremely far-reaching paper. I highly recommend you read it. We're going to look at the exact first paragraph of this paper. So I'm going to read the entire thing here. Magnitude notions are only possible where there is an antecedent general notion which admits of different specializations. According as there exists among these specializations a continuous path from one point or another to not, they form a continuous or discrete manifoldness. The individual specializations are in the first case called points, and in the second case elements of the manifoldness. Right? Okay, so the ideas here is that a space is a space of different possible specializations of an antecedent general notion. So we have a general notion, and we may specialize that general notion in many different ways. So I'm going to say that we have a space of possibilities, possible locations, that's our normal understanding of space, but also possible directions. This is what you might call the tangent space. Possible events in space and time, right? But also possible parameters or moduli that you may use to describe other sorts of things, including, right? We might think in a more general setting, and we'll see more of this later, that objects, mathematical objects of a given type, they're different possibilities. There are multiple different groups, there are multiple different rings. Those we might think of as forming a space as well. Okay. Right, the points of a space cohere in that they may fail to be separated by discrete and definite measures, right? Or they may be connected by paths. So why do paths help points cohere in this sense? Well, if you take any continuous function from the real line to a discrete set, right, like a two-element set, then it must be constant. And so we cannot give a continuous separation of the real line into two discrete classes, right? But conversely, we could also define discreteness by those spaces which the points of our purported discrete space fails to separate. So we might turn this around and say, actually, the two-element set is discrete because any continuous map from the real line must be constant into it. Right? There's a dual ways of determining what a space is. So Riemann's continuous manifoldnesses, as he describes them, right, which becomes our modern notion of manifold, but they're as they're described, they're much more similar to sheaves on the category of Euclidean spaces and smooth maps. So what such a sheaf is it's a function that takes any Euclidean space R to the n and gives you a set, and that set is a set of abstract smooth maps. So in particular, we get x assigned to R0, which is a single point, and these are the individual specializations that Riemann was talking about. But we can also take x and evaluate it at the real line, and we get the continuous paths between individual specializations that he's talking about. And in fact, if you read further on in that paper, you see that he describes the values at Rn as actually paths in the space of paths. He invents currying in that article as well. It's really cool. So we can say that x is discrete when it does not have the continuous paths between points, or rather when any continuous paths must be constant. So we can write that up here in the terms of the sheaf, but down here we can write it in an internal term, saying that x, the inclusion of constants from x to the path sheaf here is constant. And if you know the definition of this path sheaf, you can see quite easily that there's an inductive argument which will show that it's equivalent to this one up here. Okay. So simplicial sets are actually very similar to this, right? In the idea of continuous manifoldnesses, our test objects, our test spaces, were Euclidean spaces. But for simplicial sets, we can test them against the combinatorial simplices, right, which are higher dimensional triangles. So in particular, we describe them as presheaves on the simplex category of finite non-empty ordinals. And now we interpret the value of such a presheaf at n as the set of n simplices, or n-dimensional triangles in there. And we can say that x is zero skeletal when it has only zero simplices, or again internally, but now not so obviously, when internally it is true that every one simplex is constant in x. So this is true. It's not as obvious as the other one, but okay. So both of these are examples of Levier's axiomatic cohesion, which is an axiomatization that Levier gave of the notion of space cohering by essentially failing to be separated by certain measures, right? So the axiomatization says that a topos is cohesive over the category of sets when it has these four adjoints here. So we can take the underlying set of points. In this case, it's evaluating at R0. We can then have a left adjoint, which includes every set as a discrete space, and a right adjoint, which includes it as a co-discrete space, right? And similarly, for simplicial sets, we can take its set of points. We can include a set as a zero skeletal space, which is a discrete simplicial set, or as a zero co-skeletal space, where we have every possible n simplex between any n points, right? Well, exactly one. And finally, there's this extra adjoint, right? In this case, we can take the connected components of a manifold, right? And in this case, we can take the co-limit of this simplicial diagram, which turns out to give the connected components of the simplicial set. So there's a strong analogy between these two. And in fact, we can do them both at the same time. We can do them both at the same time because we can look at simplicial objects in sheaves. And now we can get rid of these two different kinds of cohesion, one after another in either direction, right? So if we have simplicial manifolds here, we can then get rid of the simplicial structure to just have these manifold-like structures, or we could get rid of the spatial structure to just have these simplicial structures here, and they both live over discrete sets. So the reason for us to go up here is that the check nerve, right, which as I mentioned was our bridge between the space and its Alexandrov nerve, the check nerve is best understood as a simplicial space. So if I have an open cover, I can bundle it all up into the disjoint union of all the open sets, which is a big space, right? It's a disjoint union of spatial things, the actual opens, and it surjects onto M in a nice way. It covers M, and then I can take the simplicial space, which it's n simplices. It's space now, not set, but space of n simplices is the disjoint union of the n-fold intersections, right? So it's all the n-fold intersections, or in other words, it's this iterated pullback over here. And that forms a simplicial space because its n simplices don't just form a set, but actually a space. Okay. So now we return to Riemann to answer our second question of what is a homotopy type? And we're just going to keep reading from the exact same paragraph. So notions whose specializations form a discrete manifoldness are so common that at least in the cultivated languages, anything being given, it is always possible to find a notion in which they are included. Hence, mathematicians might unhesitatingly found the theory of discrete magnitudes upon the postulate that certain given things are to be regarded as equivalent. Again, incredibly far-reaching paper. The main idea is that discrete notions in mathematics are to be understood by, again, they don't have paths in them, but also they are fundamentally based on having individual specializations, which we then understand what it means for them to be equivalent. And so now we can come to our definition of homotopy type. It's a loose definition. I'm not going to give a precise one here. But a homotopy type is an infinity groupoid. Right? An infinity groupoid is a higher dimensional generalization of a groupoid. So what an infinity groupoid is it has a collection of objects. So it's a notion which admits of these different specializations. And for any two objects, we have an infinity groupoid of equivalences between them. So this is a co-recursive definition. And then because these equivalences are things like that we imagine like isomorphisms, we can compose them, we can invert them, we have identities and so on. But also we have higher coherences between those, so that those laws that we're used to, like unit laws and associativity laws, they in fact are witnesses by by equivalences themselves within these infinity groupoids of equivalences. So because the equivalences form an infinity groupoid, there are equivalences between equivalences and so on. So it's actually a hard problem to express all these coherences right up, but it's a well-solved problem. So if you're looking for a specific definition, I would say that a concomplex is a great definition of an infinity groupoid. And the theory of infinity groupoids has been very well developed over the past 20 years. Ichi by Joyal and Lurie and everyone else. So the homotopy type of a topological space X, we can now give it an example of what a quote-unquote definition of what the homotopy type is, right? Well, we take the points of the space, but we're not going to identify them as they were in the original space by equality. We're going to identify them by paths. So again, this becomes a co-inductive definition. So we take 2 points, and their space of equivalences in the homotopy type is going to be the homotopy type of the path space, which is the space of all continuous paths from X to Y. So now we can see that the homotopy type of a topological space produces this infinity groupoid. Okay. So the thing I want to emphasize is that infinity groupoids are discrete. They're discrete because essentially we've killed off all the topological continuity between these points, right? They're not like in a sense totally disconnected because we know whether and how their objects are equivalent to each other, but there's no topology in this. There's no spatiality. It's just pure identity. Just as Riemann suggested, we found our theory of discrete magnitudes on. Okay. So there are many different kinds of spaces, and these higher analogs of spaces, which are spatial homotopy types, also known as stacks or sheaves of homotopy types. Here's some examples. On the left, we have the ordinary spaces, and on the right, we have their infinityization. So I guess I'm not going to go through these too much, but the main point is that all of these form sheaves of homotopy types on various sites of definition. And so as an example, if instead of taking sheaves of sets on Euclidean spaces, we take sheaves of homotopy types on Euclidean spaces, we include fully faithfully not just the manifolds, but also their higher dimensional analogs like orbifolds and Lie groupoids and other cool stuff like that. So it's a very natural generalization. And it's a good, and this is another point where we're bridging between our spaces and homotopy types now. So we have them both in the same setting. And Lever's cohesion works just as well in the infinity context as in the lower context. In fact, it works a lot better. So this is sort of an observation due to Urs Schreiber, is that if you take the infinity topos now of sheaves of homotopy types on Euclidean spaces, we still have these 4 adjoints, where now we can take the infinity groupoid of points of our space, we can include it discretely or co-discretely back in. But now, where before we had to take the set of connected components, now we can actually take the homotopy type of our space. And that becomes the furthest most left adjoint. right? And these four adjoints give us a series of an adjoint triple of monads and comonads up top, where shape here is the discrete inclusion of the homotopy type. Flat is the discrete inclusion of the underlying set of or underlying space of underlying homotopy type of points. Excuse me, and sharp is the co-discrete inclusion of the points. And so the reason that these have these names is due to Schreiber, who showed that has this fun explanation for why flat should be called flat, given that it is right adjoint to shape. So shape is a generalized term for homotopy type that's used, for example, in shape theory, which is the theory of the homotopy theory of bad spaces, essentially. So in infinity topuses, like these sheaves, one of the best things about them is that cohomology becomes representable. And in particular, various other notions, for example, bundles over manifolds become representable by objects. And this is really nice. So one of the things here is that the adjunction gives us a nice explanation for why we should call this thing flat. Is that if I have, imagine that take n to be 1 here, so that this becomes the classifying stack for Hermitian line bundles with connection. So what the adjunction says is that if I take a Hermitian line bundle with connection on X that is homotopy invariant, what does that mean? Well, it has a homotopy invariant parallel transport, right? Then that's equivalent to, well, whatever this is. And so we do know that by sort of there's classical arguments from differential geometry saying that if you have a homotopy invariant parallel transport, then the curvature of your connection must vanish or your connection must be flat. So in other words, flat of the moduli stack of bundles with connection classifies bundles with flat connection. That's why Urs calls this flat. Okay. So now I'm going to tell you about homotopy type theory because that's the setting in which we're going to prove the nerve theorem. Homotopy type theory is a logical system for working directly with sheaves of homotopy types, just as ordinary set theory or formal set theories are logical systems for working directly with sets. So the main thing to take away from here is that you can give in this logic. Everything you say about it can be interpreted as being about sheaves of homotopy types, but also it's a standalone foundation on its own. So you don't have to always think about it as being about sheaves of homotopy types, because that's actually a big cognitive load. Instead, you can take it on its own terms, and it's just a foundation. So I'm going to describe it in that way, where it's much more intuitive, right? So we can work directly with homotopy types, but as a standalone foundation, here's what it says. It says we have these things called types of mathematical objects, which is very much related to what Riemann was calling a notion, right? The types of mathematical objects includes, well, the type of natural numbers. We know what it means to be a natural number. We have the type of real numbers. We know what it means to be a real number. We have the type of sets, because we know what it means to be a set. And we have the type of real vector spaces, because we know what it means to be a real vector space. We even have a type of types, which is going to be an assumption here. And I'll just say right now, and that type theory presented in this form suffers from exactly the same paradoxes as set theory. I don't care, and I'm not going to cover them. They have exactly the same solutions as in set theory, namely you take universes. Okay. So right. So we have types of mathematical objects, which is, again, I encourage you to think of just any type of mathematical object is a type of mathematical object. And then elements of that type. So for example, which we write using a colon here. And that colon we read as A is an A. So for example, 3 is a natural number, right? Would be our way of saying that 3 colon n would be our way of saying that 3 is a natural number. And we also have variable elements. So we can say something like x squared plus 1 is a real number, given that x is a real number, right? And so we write expressions like this in type theory, where on the right here, we write our variable element and say what type it is. And on the left, we write the list of all free variables that that element depends on together with their types, right? And we can also have variable types. For example, the tangent space to a point of a manifold is a real vector space. That's what this says. Given that M is a manifold and P is a point on that manifold. So there are very few constructions we need in type theory that are all very intuitive in order to get us going. These constructions, by the way, abound in ordinary mathematics, but are not isolated as general constructions by the traditional axiomatic set theory. So it's kind of this is a nice thing to notice here, right? Is that there's sort of generalizations of common constructions, namely pairs and functions, right? So if we have a type B of X, which makes sense for any variable X of type A, right? Then we can form the type of pairs, right? Whose elements are little a in A and B in B of A, where we've substituted in A for X. So an example of this is if you have the notion of a tangent space to a point of a manifold, then the total space of the tangent bundle, right, is its elements are pairs consisting of a point of a manifold and a tangent vector to that point. So that's written using this type of pairs. Now we also have function types. And here, again, if b of x is a type that makes sense for any x of type A, then we have the type of functions, right, whose elements are functions f of x, depending on x of type A, where f of x lives in b of x for every x in A, right? And so this is, to go back to our example, if we have a function that takes a point of a manifold and gives a tangent vector at that point, that's what a vector field is. So it is true that if you that the function types always give the sections of the first projection of this pair type. But this is a very common notion that's of this type of functions where the codomain varies. Okay. Finally, we have this notion of identifications, which is how we are equivalences between objects, right? So the idea is that if you know if x and y are objects of type A, right, then an way of identifying x with y is itself a mathematical object, and therefore we should have a type of ways to identify x with y, right? So to identify the tangent space of a manifold at a point with Rn, in other words, to identify them as vector spaces, we should give a linear isomorphism. Or in other words, in this case, we could give a basis, right? So that is certainly a mathematical structure of either a linear isomorphism or a basis. So we have a type of those, and that such a thing gives us a way of identifying one vector space with another. Similarly, if we want to identify manifolds, we would use diffeomorphism. If we want to identify types, we would use a notion of equivalence, which is very much a literal translation of the notion of one-to-one correspondence into type theory. So it's a one-to-one correspondence between types as an equivalence. But then we also have, types like natural numbers, where we still know what it means to identify two natural numbers. It means to prove them equal. So we say that we have a type of ways to identify it. It's just that type is particularly simple. It has an element if they're equal, and if they're not equal, it does not have an element, right? So types that are really small like that we call propositions. Yeah.
So sorry. So does this mean that if I want to define a type A, part of what it means to really define a type A is I have to tell you what my identity types will be for that A?
So
is that something that you prove? Is this a proof or a thing you prove or a thing you define when I'm defining A?
Right. So in Bishop's constructive mathematics, he says that to define a set in mathematics, you should define the set of elements and what it means for them to be equal.
Okay.
But for us, what we note is actually you can always compute what it means to identify them from the definition of them, of the objects themselves. For example, it's like sort of the obvious isomorphisms must always be there. So because we have a very few number of constructions here, we can actually sort of inductively compute the ways to identify x with y if we take a few things for granted. Like in particular, if we take for granted that to identify two types, we give a one-to-one correspondence with them, which is known as Blavatsky's univalence axiom, then we can in fact prove all these other statements.
Okay, so these are theorems, not definitions.
These are theorems, not definitions, and also there are other systems. For example, Thorsten Altenkirch and Mike Schulman are working on a system where it will be, roughly speaking, definitional. that these things will all, roughly speaking, be definitional. And then there's also an approach to type theory called cubical, where they're theorems, but it's you don't need to assume anything except for using a more complicated type theory. So there's a number of approaches, and I'm giving sort of this informal overview. But in general, no, you always know what the equivalences are just by looking at the type. It's the quote unquote obvious ones. And that does mean if you're getting the wrong type of equivalences, you're considering X and Y as elements of the wrong type, right? And by changing the type, you also change what it means for them to be equivalent as elements of that type, right? So a good example of this is that to show that two sets are equivalent, right? To identify two sets, I give an isomorphism between them. I give a bijection between them. But to identify two subsets of a fixed set, I show that they have the same elements. So this resolves this apparent conundrum that, for example, that that the even numbers and the natural numbers have the same number of elements, right? Or that they are as abstract sets, they may be put in bijection, but as subsets of the natural numbers, of course, they're not identifiable. So it really matters which type you consider. And that's why the equality is supposed to be labeled by A. And then of course we elide A because we're lazy. Okay, so a thing I want to emphasize here is that now, just with these constructions and a few more that I have some pre-prepared slides for at the end in case you want to yell at me, with just these constructions, we can already write down types of mathematical structures. So this is the type of one-dimensional Hermitian vector spaces, one-dimensional complex vector spaces with a inner product, right? So we have a type, that type's a set. We have an addition, a zero, a scalar multiplication, and then we have the laws. And the laws, I'll have you know, these are all functions into identity types here, right? So this says, as a function that takes A, B, and C and gives me an identification like this. So this says for all A, B, and C, I have A plus B plus C equals A plus B plus C, and so on and so on and so on for all these different things, right? So now what's really cool about this is the type of one-dimensional Hermitian vector spaces, but I've denoted it BU. And the reason is because when we interpret homotopy type theory into sheaves, this type will get interpreted into the moduli stack for Hermitian line bundles. Okay? And that can be proven without too much difficulty, in fact. It's really interesting. And by the way, if you're very curious, the axiom of local triviality of a line bundle is hidden in the dimension axiom here. So you can ask me about that later. So how do we interpret homotopy type theory? Well, so there's this great dictionary, which actually goes back way further, all the way to Levere in the early 70s. And these names are in reverse chronological order, and they end before everything that's written here has actually. So all of this stuff was sort of well known deep into the 80s. But the final stuff is getting these identifications and the types to work, and that's the names you see up there. So the idea is this: we interpret a type as an object of our topo, so as a sheaf, right? And then we interpret a family of types, or a dependent type here, a type B that depends on A, as a map into it, or in other words, as an object of the slice topos, right? So really, homotopy type theory doesn't interpret into a single infinity topos. It interprets into all the slices of that topos. And that's actually why it's so powerful. Just keeping track of all our free variables lets us explicitly work with all the slices of the topos at once. And therefore, we get to do everything in the correct, internal sense with all this base change taken for granted. So what is an element? Well, an element is going to be a section of this map, which you can see has this evident interpretation as a function that takes in an element of A and gives me an element of B that lives over that same element, right? And then we can look at our two constructions. The type of pairs is given by taking the composite, right, or also known as the left adjoint to pull back. And the type of sections here, the type of functions here is interpreted as the sections here. which is the right adjoint to pullback, which exists sort of rather miraculously for all categories of sheaves. And finally, let me tell you what the type of identities is, right? So really what the type of identities is, well, first of all, note that it has two free variables, x and y. So by the above, it must be some map into x times y in the sheaf topos, right? So which map? Well, it's the diagonal, right? And so the thing I want to note is that if we are presenting these sheaves of homotopy types in the traditional foundations, we would be using something like a model structure, right? And then all of these slices would need to be not just arbitrary maps, but fibrations in that model category. And therefore, we wouldn't be taking the diagonal, but we would be taking a fibrant replacement of the diagonal, which would be a path object. And that is where we end up with the extra homotopy of our homotopy type theory. These identities form a path object in the model categorical presentation of these sheaves of homotopy types. And that goes very deep. In fact, there's a deep relationship between identity types and model structures. Okay. So now let me tell you about simplicial cohesion. We're going to go, so I've told you about homotopy type theory. Now I'm going to tell you about our two different kinds of cohesion so we can start to relate them through the nerve theorem. So simplicial cohesion is by Emily Riehl and Mike Schulman. They give well, not simplicial cohesion, but this approach to simplicial type theory is due to them. And we note by a theorem of Joyal that delta 1 is the universal total order with distinct top and bottom elements. So it's an order. Now, let me say that ordering, right, is actually the true simplex. The true simplex may be identified as the pairs of elements in the one simplex where one is less than or equal to the other. And that ordering being total says that the square, delta 1 times delta 1, is the union of its top and bottom halves, right? So either I is less than j or j is less than I, that says that less than or equal to, that says that this joint union here covers this square. Okay, and we can similarly define the n simplices as the n-fold increasing points here. And then we will assume that we have from before these different modalities. I'll come to them later, but in particular, assume we have the zero skeleton, which was you take the points and then you re-include it as a discrete simplicial space. That lets us internally recover the homotopy type of n simplices, which we can describe as the zero skeleton of the maps from delta n to x.
What does crisp mean?
It's a technical term that I'm not going to worry about. It's important for the actual type theory to work. So right, let's look at these modalities. So SK0 is the zero skeleton modality, and it is given by on n's, the n simplices is just the zero simplices. It's constant, right? And then we have, so this was like the discrete inclusion. Then we have the co-discrete inclusion, the zero co-skeleton. And this is given by saying that, well, the n simplices of the zero co-skeleton are all lists of n plus 1 points. So essentially you have exactly one for any list that you could possibly have for n simplices. And then finally, the leftmost adjoint, which is the co-limit, I've called the realization. This is sometimes known as geometric realization, but I want to emphasize that homotopy types are discrete. There's nothing geometric about this. This is the homotopy co-limit, or the co-limit of homotopy types of the simplicial diagram, which is what's written here. And we'll note that you are zero skeletal if and only if any of these three conditions hold, if and only if every one simplex is constant in the internal sense, if and only if you are isomorphic to your zero skeleton, you're equivalent to your zero skeleton, or if and only if you're equivalent to your own realization. Right? So these two are modalities, and what that means is that they are reflections into classes of simplicial objects. So in particular, the realization reflects us into zero skeletal types, meaning that it is the map from X to the realization, which is the co-limit cone itself, is the universal map into a zero skeletal type, which is the universal property of the colimit. And zero co-skeleton is reflective into zero co-skeletal types. It just means that if you map into any zero co-skeletal site, which is just a type that's equivalent to its own zero co-skeleton, you must have gone through the zero co-skeleton. It's sort of just determined on its object. Okay, so now let me give a definition of the check nerve in this setting. It's actually rather simple. It's a variant of the image. So every modality comes with a factorization system, which generalizes the surjection-injection factorization system on set. So if I have a map from X to Y, I can give its universal factorization using the co-skeleton modality. So I want to emphasize that if I replace co-skeleton 0 with exists, right? If I said, this thing here was the y's and y's such that there exists an x and x such that f of x equals y, that would be the image. So this is like the image, but with zero co-skeleton. So that's the check nerve of f. And we can compute that. I mean, it's the check nerve of f when both of these are zero skeletal, excuse me. So how does that work? Here's an example of what proofs look like in this setting, I just want to say, right? So the n simplices of the check nerve are supposed to be the n-fold pullback. So let's compute that, right? The n simplices are zero skeleton of maps from the n simplex into this thing, right? But we're mapping into a pair. So that's a pair of maps. We map into the first half and we map into the second half. But we assumed that y was zero skeletal, which means that every n simplex in it is constant. So we can replace the first half here, delta n into y, with just a point of y, and substitute that over here as well. Well, now we have that the zero co-skeleton of something zero, the zero skeleton of something zero skeletal times something else. So we can just pull that out. And now we have again zero skeleton of delta n maps into something, right? So that's the n simplices of this thing here, which is the zero co-skeleton. Zero co-skeleton is adjoint to zero skeleton, right? Or in other words, we know that what the n simplices of the zero skeleton are. This is just the n plus one-fold points of this type in here, which I'll jump to down here. So what does this last one say? Well, we've computed that the n simplices of the check nerve are a point in y and n plus 1 points in x together with identifications of f of x with y. And that is a presentation of this n-fold pullback that we described so many slides ago.
So is that a typo in the line above them where it says n instead of n plus 1?
It is brackets n, which has n plus 1 points. Yeah, that's right.
No, I'm so sorry, I implied that you made a mistake.
So as a corollary, we note that the realization of this is the image. And the reason for that is that the realization of the co-skeleton exists. In other words, there is an element, if you take the co-skeleton and you realize it, you get a type that has an element if and only if there's an element of X, right? And so if I realize this, I just sort of put it here, that becomes exists, there's my image. Which means that this is all surjections are effective epimorphisms here. Yeah.
What happens if you just replace co-skeleton with skeleton? What do you get?
It works a little differently. I'm not sure what you get. I think what you get in this case is
like if you assume things to be zero co-skeletal and take skeleton here or something, do you get something interesting?
Yeah, I'm not sure.
Me neither.
So one thing I will note is that you don't get like skeleton is not a modality, it's a comodality. So you don't get this nice factorization system coming out of it. So if you put the realization in there, you would get something also interesting. But yeah, okay, anyway. So now let's talk about the nerve of an open cover. So suppose we have a cover of M, our space. So again, we can take the disjoint union over the indices. By the way, this is just fancy notation in type theory for the pair type again, of a pair of an index and an element in the indexed type. And that is a surjection, right? Because it's a cover. So in particular, n equals the image of that thing, which as we saw is the realization of the check nerve of that thing, right? So we know that n is equal to the realization of the check nerve of any cover of it. It doesn't have to be open, in fact, we'll see. But the nerve of the cover, then, right, it's going to be the simplicial set, which has an n simplex for every inhabited n+1 fold intersection. Remember that all the way back from the beginning of the talk. So how do we construct that this way? Well, we have our factorization of C through the check nerve, right? We also have that this is bundled over I, the indexing type, by projecting out the first component. We can also factor the terminal map here into the co-skeleton here. And so we get that this check nerve is actually bundled over the co-skeleton of I. And remember that the n simplices of the co-skeleton are the n+1 points in I. So the fibers of this map are the n+1 over a fixed n simplex here, are the elements in that intersection. Right? So in particular, the nerve is going to be the image of this projection. We're going to take only those n+1 points in I, for which there exists an element in the intersection. So that's how we can define the nerve of the Alexandrov nerve of an open cover, modally. It's quite nice. So now we can say what it means for a cover to be good. And remember that a cover is good when its n+1 fold intersections are contractible if and only if they're inhabited, whenever they're inhabited. So what does that mean? Well, if from the n+1 fold intersection, we can always take its homotopy type. And if you have an element of the homotopy type, then you certainly have an element. So there is a map from the homotopy type to the type that expresses the fact that there exists an element in here. And we can ask that this be an isomorphism or an equivalence, right? In other words, the homotopy type is inhabited, is a point if and only if there's an element in it, right? So we can then prove a little lemma that sort of externalizes this. This is expressed for each n+1 fold intersection. But we can also say that C is good if and only if the homotopy type of the check nerve is equal to the image. Right? Why? Well, basically, we've said that we could replace shape here with exists. And we know that the n simplices of the nerve are the elements here such that there exists. We replace it with the shape. We then note that the I being a discrete set, and I didn't say that, but we have to discretely index our cover for this to work. We can just sort of move the homotopy type through that. The homotopy type of a discrete thing is the same thing. So that's how we compute this lemma here. Right, and now we're ready to put it all together. Almost. So now the thing I want to note is that we actually have, we've been using these different modal systems, right? So we've been using both of, this is where I'm actually talking about the type theory, although I think I'm going to skip through it. We've seen realization zero skeleton, zero co-skeleton, shape, flat, and sharp from the spatial aspects, and they both work at the same time on simplicial spaces, which the check nerve is, right? Okay. So now, right, in commuting cohesion, we call these things focuses. These are local toposes in particular, and this is the focal point. So we call these focuses. And then the type theory, which Mitchell really came up with, is an extension of Mike Schulman's type theory for cohesion homotopy type theory, where we allow multiple focuses. And something is said to be crisp when it's in focus. And so for something to be simplicially crisp means that it's in the simplicial focus, which means that it does not depend non-trivially on simplicial things. But I'm not going to focus on this. It's just that we have it's a real type theory. It's kind of nice. It actually builds in the rules for crisp induction principles. If you've read Mike's paper, it's actually kind of convenient the way this presentation. It's actually, I think, a nicer presentation of the type theory, even if you're only using one focus. It is also can be, I suppose, mimicked by the modal type theories of, for example, Danny Gratzer and Mike Schulman's later variation. Okay, so now I have to go into how do these things relate, right? So we're going to finally prove the nerve theorem on this slide, by the way. So how do these different cohesions relate? Well, note that R is zero skeletal. It is simplicially discrete, right? It's a set. And delta 1 is spatially discrete. It has no paths in it. Because of this, these two cohesions are orthogonal, and they slide past each other. And in particular, the localizations, the shape and the realization commute. And in fact, shape is computed pointwise, which is not totally obvious, but is true, just because this is a diagram. The simplicial cohesion is expressed as a diagram category, it's just functored. So it actually slides past all the spatial ones. And also we note that the homotopy type of a proposition it's just a proposition. That's not important for this. Just using this first one is what we really need to prove the nerve theorem. And now we have a really slick proof of the nerve theorem. If you have a good cover, right, then the homotopy type of your space is the realization of its nerve, right? How do we do this? Well, the homotopy type of the space is the homotopy type of the realization of the check nerve. Why? Because the realization of the check nerve is M, because C is surjective, right? Then we use this fact, the orthogonality of the two cohesions, we can slide the realization past the shape, and we find that we have the realization of the shape of the check nerve. But as we noted, a cover is good if and only if the shape of its check nerve is its Alexandrov nerve. So we're at there. That's the nerve theorem. And as you can see, this was really general. So we can give a more general formulation of it. If we have any localization which commutes past the realization, we get a nerve theorem for it by the exact same argument. And if you have all these other features, you can show that that good can be characterized in this element-wise way, as saying the n-fold localization, the n-fold intersections are L-local. So commuting with realization is sort of like saying you're a infinity pre-topos morphism. Yeah, so I would love to know of other good use cases for this. So if you have any, please do let me know. So I should note that nothing really trades, even in this part, on the real line being the real line, this cover being open or anything. It's quite general, right? Okay, that's all. Thank you very much.
Thank you very much, David. Let's pass it on to the audience for questions. If anyone has any questions. Oh, yes, Tim. I have a question. Can you go back one slide? So something that confuses me is like, the whole way you build homotopy type theory is like very much based, from my understanding, on like this like prototypical example of, right, like R is contractible, R is, or like, that's key, that's cool. That's what like contractible means. And sorry, I'm trying to phrase this question well. What I don't understand is, say I want to care about two different geometries, which are both classically like really annoying to prove the nerve theorem for. So I might want to do like n-fold smooth, like Cn functions, or I might want to do holomorphic. In both cases, I have kind of two issues to worry about. One is my definition of contractibility will be different. Like in the Cn case, I want to say something isn't just contractible, I want it to be like n-smooth contractible. And in the holomorphic case, I want to say something even more gross, which is I would like to say holomorphically contractible, which is actually about an existence of a certain holomorphic function. It's not really anything to do with topological contractibility. And then the other thing that's gross is what my definition of good cover is. So and like, for example, in one case, your good cover will be things which are like, you just say exactly the same thing. You say like the intersections are n-smooth contractible. And in the other case, you'd say that they are like Stein. You have to start using words like Stein. So I see how the good cover part is hopefully encapsulated by changing modalities using this L thing. But this first part, where my like very notion of contractibility is somehow different, does that mean that I should be changing homotopy type theory, or is that also something that builds into the modalities?
No, so that is so when I say contractible here, I mean contractible as tested by this real line object. And this real line object, in the story I was telling here, this real line object is actually the smooth real line for smooth things. That's just how I told the story. It doesn't have to be. Which means that this is the smooth nerve theorem, the one I was telling.
Okay.
It actually is very, very it's very, this story is extremely amenable to whichever different kinds of real thing you want, essentially, because they all present the same homotopy type rather naturally. But in particular, this R here is your representable real line. from your site. So it is the CN real line if you're doing that. And then and nothing about this trades on that. The definition of the homotopy type here is localization at that real line object.
Okay.
Right? So, but it doesn't have to be defined like that. When we generalize, right? This modality could be defined anyway. It would be nice if it was accessible, meaning that it is presented by a localization at some small class of things. And it has to commute with the realization, which is a pretty strong constraint, right? Relatively. And that follows if it's given by the localization at a family of simplicially discrete objects, which is not so bad. But that may not be so in the holomorphic case, because in the holomorphic case, I'm not sure that it may be enough to kill all polydisks or something like this, but I'm not totally sure exactly what the correct definition is, but I would love to know.
So this is one of the things I would love this to clear up is like I could think of two good definitions of good cover, and one would involve polydisks, one would involve Stein.
Right.
And yeah.
So but the definition of good always comes from L. To be L contractible means that when you apply L to your sheaf, it becomes a point.
Okay.
And so to be good, the correct definition of being good is that L of the check nerve equals, it's this last step, L of the check nerve equals the nerve, right? Okay. That's what good means. If you want good to mean anything about the actual n-fold intersections, you do need the rest of this. They show up in that proof. And so, but these are not, this comes from the commutation with finite products, so it should be pretty easy. This also should be straightforward if L is like defined on the underlying space, on the underlying thing that you're taking simplicial objects in. And this last one means that L is like a global modality, meaning that it's not, for example, it's not a topological modality, it's a it's something like cotopological. So what that means is that it's not like restricting to an open on a sheaf topos or something like that. Or it's not restriction to a subtopos. It's something that
something we can chat about afterwards. I have a definition of good in terms of a topos, and it doesn't use good. I'd like to talk about.
I would love to see how that relates. In particular, getting this to work for the holomorphic case is something that is particularly interesting. And other things like maybe A1 and stuff like that. A1 should sort of work pretty straightforwardly. The question is, can you actually give a good example of a good open cover? I think the hard part turns out to be in bad geometries or like difficult geometries is just giving good open covers. In fact, the existence of good open covers for manifolds is not a trivial theorem. No. So yeah, it turns out the easy part of the nerve theorem is the nerve theorem.
Exactly. The hard part is the existence of the covers.
Exactly. No.
Okay. Thank you. Any other questions?
Jason might have one. I'm not sure if the chat has anything.
True. Let's just check the chat quickly. No, it seems like there's no questions in the chat.
Yeah.
In that case, let us thank our speaker again. Thank you.